My name is Aaron Dotson. I'm a professor in civil engineering at the University of Alaska Anchorage. I'll share a little bit in this presentation about cold regions design considerations for how water and wastewater must be distributed in a small community that's cold, as well as collected from a wastewater perspective in that same community. In Alaska, where I am from, we have a lot of water and wastewater systems. In particular, this slide shows the water systems that we have. The interesting part about our state is while we have about 500,000 people in the state, majority of our water systems serve only between 100 and 300 people. Further, these communities that serve 100 to 300 people are very widely distributed and in very cold regions. So with their remoteness and disconnected from the road system and the small size, it makes it quite a challenge and quite expensive to provide water and wastewater service. So here's some example of a community named Kipnuk. It's out in the southwest Alaska. And this community has no running water, no piped sewer. They have a watering point in the middle of town, and they use honey buckets or 5-gallon bucket as a place to go to the bathroom. All the water that comes into the home is hand carried. The reason they do not have piped water is because where they live, the ground is unstable. It has intermittent permafrost, as well as is quite soggy in the summer from water. And with that, there's no roads. They have small vehicles, four-wheelers or snow machines that travel on boardwalks through the town. So with that in mind, having plumbing conveying water to and from a home makes it a challenge. Further, in a community like this, deliveries of goods come either by small aircraft or by seasonal barge, with the ability to only have small shipments or once a year large shipments. Providing the equipment and or materials to have a large water and wastewater system can be a problem. So as I said, with the context of remote communities, our communities in rural Alaska, especially the ones that are between 1 and 300 people, are not connected by road. They receive seasonal barges for large goods. They do have air transport for regular transportation to and from the village, but that makes it a challenge to get large engineering pieces of equipment in, large pieces of pipe, pumps, others. It's a challenge to load that into a small plane. Beyond that, in the community, some have small vehicles like four-wheelers and snow machines. Some few have large vehicles like a normal sized car. And everyone uses the river system or the ocean when it's not frozen with a boat, or when it's frozen with other means of transportation. So if you can imagine a water and wastewater system that must be operated and maintained by someone that only has something not much more sophisticated than a motorbike, this is the type of system these communities need to have unless they have the capacity to have a larger system. So I'm going to share a couple other pieces that make this a challenge. Another piece that makes these rural water systems a challenge is because they're just disconnected from the road system, they're regularly disconnected from a large-scale power grid. With that in mind, these communities use diesel fuel for powering the community, creating electricity from a generator, as well as at times have to use either wood or fuel oil to heat their home. And so now we think about this water system that needs to move water around using pumps and energy, possibly heating the water to keep it from freezing. That takes a lot of diesel fuel. That diesel fuel has to come in on that seasonal barge. So we need to assess the energy load that our water and our wastewater system takes on when it comes to the amount of fuel the community uses. And as I had mentioned, the soil makes a big difference. When you are in a non-permafrost related location, you can dig in the ground, you can bury your pipe, you can mount your pipe or your structures on top of the ground because your soil is stable. In the case where you have frozen soils or permafrost, this becomes much more complex. In this picture, we have a number of photos illustrating what frozen soils look like, either as a soil core with an ice lens or failures that have occurred due to ice. Either ice causing the soil surface to slump or ice causing the soil surface to rise. And if you think about it from the perspective of these different dynamic situations the ground is causing, this means that if you put infrastructure on the ground in a frozen area, that infrastructure is likely to move, whether it be up or down, and it's likely to move seasonally. So how do you design your system to handle this changing and very dynamic ground situation? So to sum up, the idea here is cold regions plus limited access plus frozen ground makes it all around a challenging situation to build water and wastewater systems in. If we think about how people used to live in these areas, as shown in the picture, life was much more simple. Now, if we want water delivered to our house, free flowing, and wastewater drawn from our house, free flowing, we have to really think about what that means. So when we think about what it means to have a water and sewer service, we have to understand how much water is being used. If we have very little access to water, say I have to go get my water from a watering point in town, I'm going to use very little water because I'm not going to want to carry it. In those cases, these self-haul systems, people use between 1 and 5 gallons per person per day. And as you increase the type of system or the complexity of the system and their ability to make the water easier and easier to get for a homeowner or make it available in the home, the amount of water used per person per day increases. So as it increases, we gain health benefits. Self-haul, people limit their water use to what is most important to them. That's usually a bit of washing and drinking. As we increase the amount of water available in the home, people tend to do more hygiene practices, creating a more healthy environment. So what do these practices look like? Here's some images of what self-haul would look like. You can self-haul by going to a local watering point in your community. In rural Alaska, these are called washaterias, where there's a watering point, oftentimes a toilet and a laundry machine, and possibly community showers. So if you go to that watering point, you can use the facilities and bring some water home to you, to your house. But it's still hard to carry. Hopefully you have a snow machine or a four-wheeler to take it home with you. What could be easier is in the summer when rain is available, you can put buckets under your rooftop and collect rainwater. That means all you have to do is go outside your door to collect the water. That's great. People prefer rainwater over most of the community water because of the natural taste of it. Further, while harder to get, ice melt is pretty common in communities in rural Alaska because it's a traditional source of water. So people travel out to a region or a lake or a pond that has some traditional history, and they chip ice out of that lake and bring it home. Again, while heavy, it provides a traditional connection. But you're not going to get hundreds of gallons of water from ice. As we develop into larger systems, if there's a road structure in the community or road infrastructure, you can have a small vehicle haul. This would be something like a four-wheeler or a tiny tractor that would be carrying a water tank that would collect water at a watering point, bring it to your home, and deliver it to a small water tank. This makes it sure that you have more water at home available for those hygiene needs, and that it's easier for you because you're likely paying for this as a service. The challenge comes is if there is a snowdrift or access block to your tank, it may get harder and harder to get your water delivered to you. As we go into a bigger community, we might be able to have a large vehicle haul. This would be a large truck, something that you could see on a normal highway in a larger city. The challenge with this is that while it's possible to have these in a community with adequate road infrastructure, you may have local regulation that says that people driving a vehicle over 1 ton need to have adequate driver's licenses. And in that case, you might have a capacity issue in the community. In both these self-haul or small vehicle haul or large vehicle haul cases, the vehicle is acting as the conveyance system, kind of a drivable pipe. Similarly to water, as I've mentioned here, wastewater is handled the same way, where you draw water from a tank into a vehicle similar to the ones shown here. If you decide that you need to go to a pipe, or this is what your community has the ground to support, the desire and ability to tolerate the cost, you're going to look at something that uses primarily Arctic pipe to convey the water. Here's a picture of Arctic pipe, which is a pipe in the center here, shown as an HDPE pipe, nestled in a block of insulation to help modulate temperature, and jacketed by a galvanized band or a galvanized sheath. In this piece of pipe, we insulate it to keep the warm water or the wet water inside the pipe or sewage wet, and we keep the cold out. In most of the cases, we oftentimes put other type of appenditures, something like tubes for a glycol heat loop or an electrical heat tape, so that if there was a freeze issue, that you could locally unthaw that piece of pipe. This type of pipe is quite expensive, but it does work in the Arctic. So how do we mount this pipe? In a system or a community that has frozen ground, possibly permafrost or discontinuous permafrost, you may decide to mount your pipe above ground. If you mount your pipe above ground, we have to worry about how does the pipe hinder foot traffic or car traffic or small vehicle traffic through that community. Further, not only does it hinder vehicle traffic, it hinders people. So when we hinder the people walking around, we need to provide means for access. Here's an example how we may build a footbridge over a section of pipe. Further, the other catch is if you have this jacketed pipe above ground in the summer sun, not only now do you have to deal with the pipe being cold in the winter, but that jacket being warm in the summer may mean that the pipe wants to expand. So you need to be careful in the way you design your system to handle flexibility, both in the ground moving as well as the pipe flexing due to thermal gain by the sun. If you decide to bury your pipe, we need to be careful at how we bury that pipe in frozen soil. Do we bury that pipe in the active layer, the area of the ground that freezes and thaws every year, or do we bury that pipe in permafrost? If you decide to bury your pipe in permafrost, you must do your construction in the winter so that the ground stays frozen during installation and after. The catch there is you need to make sure that your pipe is insulated adequately to keep the water wet, but not let the heat of the water out into the permafrost, as well as keep the cold from the permafrost from getting to the pipe. So you need to do your math well. If you decide to bury your pipe in the active layer and it's insulated, you need to understand how that ground movement may affect your pipe. This is more a problem in sewage pipes when you have to think about gravity systems, and if you have your pipe change and go uphill due to ground motion, that the sewage can still get from point A to point B. If you decide to bury it below the active layer, this is when you bury it below the frost depth in most places. In the Arctic, that may be very, very deep. In Anchorage, which is subarctic, we have to bury our pipe about 12 feet underground, or about 3 meters deep, 3.5 meters, so that we can make sure that that pipe is in thawed ground and it is unlikely to freeze. This makes it a challenge for breaks and winter repairs. If you do have a leak that you identify in the winter, digging through 12 feet of earth to get to your pipe is quite challenging. So if you decide to bury your pipe deep, you need to look at how much infrastructure, be it a backhoe or a steam truck or a vacuum truck, do you need in the community to be able to do repairs year-round. Now that we know that we have pipe that we can either put above ground or below ground, another form of freeze protection is recirculation, or keeping the water moving. Here's an example of a fast main distribution system which uses pit orifices. In this instance, at the water treatment plant, you pump the water out into the main line. The water leaves and goes into a main loop around the community. That main loop is traveling at about 5 feet per second. And it provides the motion in the water so it doesn't freeze. Once it reaches a home, similar to the main, you need to recirculate the water in and out of the home service line. So in this case, with a pit orifice, this pit orifice scoops the water into the service line, it goes through the home, and then it goes back out into the distribution system. In this instance, we use a large pump in the water treatment plant, which the municipality owns, and all the energy of this system gets covered by that one large pump. A more modern system is a slow main system where we distribute the energy usage. In this example, we don't have to pump the water as fast in the main. We only pump the water between 1 and 3 feet per second. And then now when it reaches a home, instead of being scooped up by a pit orifice, we use a small pump, a recirculator pump that is often used in water boilers for home heating, to draw the water out of the pipe, recirculate it through the service line, and return it to the main. In this instance, the municipality has less of an energy footprint for their pump, but the homeowner has a small energy footprint of their own to keep their own service line on operation. If we decide that we need to think about how do we group our utilities together to gain benefit from the wastewater being warm to keep the water thawed or warm, we may use something like a utilidor. A utilidor is like a large hallway that's built, either a box or even as big as a hallway you could walk in, where we mount all of our pipes. This is an access way where we mount the water, the sewer, possibly a district heating system. And in this instance, all of this infrastructure shares its heat load to keep the water wet in the drinking water, keep the sewage from freezing, and again, to provide possibly district heat. These are great because they keep all the utilities together, but they're also a challenge because, again, it's a large piece of concrete or infrastructure that has to flow through the city. If you do have a utilidor system, you need to consider how that utilidor keeps its heat inside the utilidor. If that utilidor is too hot, it may thaw the ground, and if that thawed ground may cause a safety hazard in your community. So use the heat wisely, use it to keep it warm, but not release the heat into the environment. Once the water is delivered to a home, we need to consider now the distribution system is usually very rigid because it's buried in the ground, it's anchored in heavy infrastructure. Your house is usually less rigid, possibly on post and pad type of foundation. If your house moves and the water mains and the wastewater lines do not move, the connection at your house may become loose. This is an example of an Arctic box that's used in Alaska. And now we've gone to different alternative designs to help that box stay on your house better during this movement that is caused through winter freeze thaw. So understand that connection. If it separates from the house, we need to keep insulation in that connection. Further, now that we move a little bit out of the piping realm and move into the tank realm, if we have a tank that holds our water in the community, we want to make sure that tank makes our water available for people in high demand at times, as well as for firefighting. The challenge is if we have a large tank of water that's located above ground, in the elements in the winter, it becomes quite cold. We heat that tank or we recirculate that tank to maintain a water temperature above freezing. If the water is above freezing, that means there's heat from the water that is going to escape, and it might escape into the ground. If that ground is frozen or if that tank is mounted near permafrost, we may need to analyze how the heat is distributed from the tank into the ground to keep the ground from failing and make sure our tank stays intact. And moreover, if we design, whatever we design in these cold regions to distribute water and to collect water, we need to understand what might happen during a failure and how we might repair it. Here's an example of a water main that's crossing over a footbridge in a small village that had a leak. That leak caused a large ice sculpture, but that ice sculpture is going to have to be removed before maintenance is performed. That's going to take a lot of effort to break that pipe up, or break the ice apart without breaking apart the pipe. So make sure that when a system is designed in a community that we have the tools not only to install it, but to handle failures when they occur, especially the coldest day of the year. So with this presentation, I shared a lot about how these systems work in Alaska. These last two pictures are of Longyearbyen and Svalbard. They have a similar piping network where they use Arctic pipe that's jacketed in HDPE and use many of these same theories to keep their water system from freezing, as well as their wastewater. So this is a very common methodology for water and wastewater distribution in cold regions. Thank you.